Hello, testing, testing. Yeah, hey. Hoo. Here we are. Good morning. Sorry, no. Wait. It's the afternoon. Good afternoon, everyone. How's everyone doing? I am doing really good, thank you. And what about yourselves? How many people do we have? Oh, we have a few people here. Hi, good afternoon, whoever you are. I don't know if you know, but I can't really see. I can't really see who is on the video as I am streaming, unless you talk on the chat. Like for example, Andres, good afternoon. Yes, where is this? Here. I actually just finished it like right now. Oh, that was gross. The last sip with all the tiny particles of that was not nice. Oh, oh. Yes, I think, and that color is a little more balanced. Andres, good afternoon. Good to see you, sir. And when are when is my coffee coming showing up in Cambridge? Huh? My nice Colombian coffee from Medellin. Huh? Sometime. Hopefully, maybe in the real world. Maybe we get to hang out in the real world sometime. That would be great. Andres, did you go to the Arcadia that happened in Mexico City? Were you around in the country already for that? That would have been nice to meet there. That was a fun Arcadia. I had a lot of fun there. Very nice one. What are we? So what are we doing today? Well, let me start by the basics. So let me start by the basics, which is good afternoon, everyone. This is Jose Luis. We are here at Parametric Camp. At Parametric Camp, what we do is... you were in Texas. I was in Texas too. Did we meet? Did we actually meet there? I don't think we met in person, did we? Anyway, sorry. So this is Jose Luis. This is Parametric Camp. We do computational design live streams. We go live and then we hang out, we talk on the chat, we do some social, but mostly what we do is we record tutorials live that then we edit, we trim, we chop, whatever, and then we put them together as more edited, more like streamlined content. Like, because when I'm recording, I'm a little woozy, I'm a little like, whoa, whatever, yabby. And as you will see very soon, if you're new to the channel. And then so if you wanna join us, make sure perhaps to subscribe to this channel and to hit notifications so that you know when we go live. You can also figure out when we go live by following us on social media, or you can also subscribe to a Google Calendar that we have. I'm putting the link right now on the chat. And if you also want to get closer to the community, we have a Discord server where we have conversations throughout the week. There's a channel for introductions and people tell a little bit of who they are, why they're here, etc., etc. I like getting to know the community. I'm very happy that I get to know many of the people that are part of the community. Like I know Andres, and I've been seeing Hanie that's been joining us very recently this week, because this week and last week, what we've been doing is we typically just stream once a week, typically on Fridays. But I'm working on a series that is called Introduction to Parametric Modeling that I really want to finish, and I'm kind of like rolling into just getting this done. So I think it's going to happen. I think I'm going to be streaming. I streamed all day last week. I'm going to be streaming this week. And if I have to take a little bit of time next week, I will, because I really want to wrap this up and then have content ready for anyone who wants to learn the basics of parametric modeling. And similar, I'm getting to know Nyland, who has joined us very recently. He introduced himself also very recently on the Discord channel. Looking forward for the in-person Parametric Camp meetup. Wish I joined UTA back in 2019. Because what happened? You were admitted, but you didn't? No, but you said that you were going to... You said that you were going to join UTA sometime soon, correct? Weren't you going to do that this fall? Yeah, you can do it this fall. So yeah, hopefully we'll get to meet in person at some point. I'm not sure if we're ever going to organize a parametric camp in-person gathering anytime soon, because also the community is very international, so I'm not sure how would we do that, but we've definitely had online meetups. We did one last December. It was just a Zoom call. We all jumped in and we were hanging out and we got to talk and we streamed it as well. It was a lot of fun, actually. Andres was there, right? Weren't you there, Andres? And oh, 2009, you're right, because they hosted Arcadia. I was there. That was a really nice Arcadia too. Arcadias are typically very nice in general. I don't remember one that I was like, but what am I going to say? I'm in the board of directors of Arcadia now, so. But I do actually believe that it's a really, really nice event, and I enjoy it a lot when I go. So hopefully that will happen soon. I'm actually, for those of you who may not know that, I'm in the board of directors for this year and next year, and I'm also co-chairing with a lot of wonderful people. We are co-chairing the online conference for this year. So, which is going to be amazing. And we have a lineup of keynotes and workshops that is going to be amazing. And of course, the research that people bring as papers is also amazing as well. And so we hope to make a really, really nice event. We will be online, but hopefully it will be the last purely online event that we throw. And in 2022, we will hopefully go back to in-person or some hybrid model or something where we can actually get together physically. Now, what are we doing today? So, what do I have on the roster? Yes, so we're doing beams, we're doing trusses today. We are right now by the middle end of the series, I would say. We did, for those of you who might be new, we've learned the basics of the basics of Rhino and Grasshopper, the interface and all those things. We've learned basic geometry types like vectors, points, planes, and NURBS geometry types like curves and surfaces, and how to operate and manipulate many of them. So that has been quite interesting. And what we've done as well is that we have looked at how to manipulate data in computational design workflows. We have looked at the particular case of data structures in Grasshopper and how they work. We've looked at data trees, and we recently, yesterday, we took a look at lists, which are also kind of specific to Grasshopper, but they're way more generic than data trees, which are really, really specific to Grasshopper. So today, we're going to do a series of examples to refresh and to improve our to improve what? We're going to do a series of examples to improve the way we work with lists. That's not a fair way to say it. What we're going to do is we're going to do a few examples where we're going to practice messing with lists, getting elements, removing elements, chopping elements, etc., etc. So that's going to be quite interesting, I would say, actually. My opinion, my personal opinion. So now what are we going to do? What are we going to do? Yes, so we're going to start with a Pratt Press. And it's a little hot here. I'm going to open the window. I hope I don't get construction work noise. I recently changed my office, by the way. I'm in a new office and I have a new light system. How is the light? How are you liking the light? How is the light looking on my face? You know? Because I have a new light system. I knew that I need to get a new desk. It's getting really small. And I also need to get a bigger green screen so that when I do this, my arms don't cut out and I can open my arms bigger. I'm working on that. Hopefully sometime very soon. What do you guys think? What other improvements could we do to the channel or the way we stream? Think about it and feel free to type something on the chat or whatever. So let's get started. So I'm going to fire some Rhino. I'm going to fire some Rhino here. Okay, and then I am going to I'm going to fire this. And then today, what were we doing? We're doing a Pratt. We did a Virendel. Last exercise, we did a Virendel Truss Tarike. Good to see you. Thank you for your kind words. So Virendel Truss, usage right, Creative Commons. So we did this, and then I would like to do today. We're going to do a Pratt Press, which is going to be the typical truss. Or it's more like a Hoey truss. I don't know. It's a typical truss that has, or should it be a Hoey? Or maybe it's a Hoey truss. What we're doing, because this looks more like the. Wait, so Hoey. Oh, how do you pronounce this? How? As the vertical intention and diagonal members are in compression. Was invented by. Okay. Oops, I disconnected. Uh-oh, I disconnected from my wireless display for some reason. Oh no. Sorry, for some reason my sketchbook got disconnected. So let me reconnect again, and you might see some flashing on your end. Yep. Yes. Okay, so that's good. What is a Pratt Press? What? Why is this? What is going on? Why am I disconnecting? Huh. Excuse me, I am having technical problems. For some reason, my sketchbook, the one that I use for sketching, is disconnecting. I don't know. Okay, so, all right. Okie dokie. So, we're just going to do Pratt and whatever. Elements are going to be intention and okay. Okay, so how are we going to do this? Well, like we did before, I would like to make a diagram first, and then I would like to make a diagram first and explain what are we going to do here. So I'm going to explain. Well, we're going to first start with a support. Oh, not green. We're going to first start with a support, and we're going to start with another support. So that's going, and then what we would like to do is we would like to draw a truss that is going to be something like this, and then it's going to be something like this, and then it's going to be like this. 1, 2. Oh, that's a terrible sketch. And then something like this, and then like this, and like this. Okay? So, and then what things that we would like to control are going to be the typical things. So are going to be the length, which is kind of going to be defined by the supports, the number of spans, which is going to be the number of spans, and then the depth, which is going to be the length divided by a factor. And this factor is the one that we're going to be controlling. So that's going to be it. And then what we probably want to do is we will need to create something that is going to be, first, we would like to create the line, and then we will need to find first all those points, and then create all those points, and then once we have them, we will need to join them in various ways. So, and then at that point, as soon as I get that, I can probably go back to the, as soon as I explain this, and then I do it in Grasshopper, I can go back and explain how we're going to continue and how we're going to do the data matching. That probably sounds good to me. Tariq, King Post, what does that mean? Taufik, welcome to the channel. Are you new here? Join us on Discord and make sure to introduce yourself and say a few words about yourself so that we can get to know each other. And the previous videos you can check if you look at our main channel. You can probably see, if you look at our main channel, where are we? If you look at our main channel, you can see all the videos that we have published so far, and there's a playlist called Introduction to Parametric Modeling, where we're publishing every day. We publish one of the new videos that we have recorded. And if you want to see all the material before it gets published as a video, just make sure to check the live streams, where we are just like recording. And no, welcome. How are you doing, sir? You guys know, what? No, good to see you, man. Thanks for coming. It's always a pleasure. So let's get started. I'm going to start here, I think. Okay. Okay. I'm not sure what this is. I'm not sure where this image came from, but I like it. Oh, I like this one actually. Okay. Okay, dokie. So what are we doing? Let's get started. Wonderful. Let's get started. So the first thing I want to say is that I'm actually not sure if what we're going to do is a Pratt truss or a Howe truss, because it turns out that the main difference between the two is whether if the diagonals work in tension, which is the case of the Pratt truss, or whether if the diagonals work in compression, which is the case of the Howe truss. But that is the case if you draw the truss like this, as if it was a bridge, but we're actually going to draw it upside down, as if it was supporting some kind of flat roof or like some kind of long span on top of it. And if we flip it, the behavior of the diagonals is going to change. Here, they're going to become in compression, and here they will become in tension. So I guess the most technical right way of saying this would be that we're going to do an inverted Howe truss, but I'm actually not sure if that is even a thing. So whatever, I'm just going to call it Pratt truss because the way we're going to design it is that the bars are going to be in tension, which is, I believe, the spirit of this particular arrangement here, even though it's going to be flipped upside down. So, and then as in the previous video where we did the Virendel Truss, what we're going to do is we're going to work with a very similar set of inputs. We're going to assume that we have 2 points somewhere in Rhino or that are coming from our architectural design, whatever, which are the supports, which is where the truss needs to anchor. And then our task is to generate parametrically this shape here, which is going to be, you see that the Howe truss upside down, where each one of the diagonals is going to be working in tension. The things that we will want to control are going to be very similar to the previous exercise. We will want to control the length, but not directly as a number, but just implicitly as the dimension between the two starting and end supports, which are the ones that we're actually going to control. So we're going to control the length only implicitly as we move the points around in 3D space. We will want to control the amount of spans that we have. And for this one, just to make it a little easier, we're going to force that the number of spans is going to be even so that we don't have to deal with a special case of odd spans, and therefore what happens with the middle span. Which way does the diagonal go, or if we make a cross, which could also be a situation. And then we will control also the depth of the truss. And as in the previous example, we're not going to control it directly with a parameter, with a number, but we're going to control it with a factor. So the depth is always going to be a factor of the length. So 1/10 of the length, 1/12 of the length, 1/16 of the length, which is very commonly how it's done, how elements are pre-dimensioned in structures. And also this way, if we make the span between the supports larger or bigger, the depth will also adapt dynamically, which I think is also really nice. So we're going to do that, we're going to control that. And then roughly, the process that we will need to follow is we will first need to create a set of points between the two supports that corresponds to how many spans we have. And then we will need to set another collection of points underneath without the extreme ones, so that, and those are the points on the bottom of the truss. And then, as you can already see coming, we will need to do a little bit of data manipulation to make sure that we join the right collections of points with the right collections of points. So how do we do the vertical chords? So the top chords, the bottom chords, the vertical bars, and then how do we do the diagonals? So it's going to be like 5 families of bars, if you will, because remember, because we are thinking of designing this as part of our structural engineering work, we're going to imagine we're structural engineers here, because this model will go to a hypothetical structural and calculation software. What we will need is the single lines. We don't really care about surfaces or the volume of these things, but we will need individual lines between each one of the nodes. So having one continuous line between the two supports will not work for this particular exercise. If you want to learn more about why that's important, make sure you check our previous video, our previous exercise in this series, the Virendel Truss. So before we get into the nitty-gritties of list manipulation, let's just get started with the simple thing, which is creating the the parameters and creating all the points on the top and the points at the bottom. And then we'll come back and keep some thinking to how are we going to organize and move things around to create the different families of bars that will be in this truss. Okay, so boom, out. So we are going to, what are we going to do? We're going to open the, I'm going to stop Dropbox, otherwise it's going to blow up. Huh. Oh yes, okay. So this is going to be exercise. We're going to open this now, and then we're going to save this as E16 Pratt Press, for example. And then here, I'm going to do something very similar. Oh, wait. Oh, okay, so I'm going to save that, and then I'm going to save the document as E16 Pratt Press. Okay, and then I'm just going to remove all of this stuff here. Okay. I think I'm going to start like this. And actually, okay. All right. So let's get started again. Okay. We're going to start the exercise in a very similar way that we started the previous one, the Virendel Truss. And if you remember, I created two physical points in Rhino that I brought in here as using point empty containers. And then I created a line between them. I subdivided the line in a particular amount of spans that I can control. And just slightly differently than from the previous exercise, what I'm going to do in this one is that I'm going to make sure that the number of spans is forced to be an even number. So I'm going to right click on the slider, I'm going to edit it, and I'm going to click here on even numbers. And therefore, now the next one has to be 8, 10, etc. So I make sure that there is no uneven amount, there is no one central span, just to make things a little easier on my end. And then if you remember also, in order to calculate the depth of the beam, what we did was we took the line, we calculated its length with the curve length component, and let me just please add here a bifocals. And then after that, we created an expression to calculate the depth of the beam as to the depth of the beam like this. So this depth is going to be equal to the length of the curve divided by a factor. A factor that for us was going to be a parameter. So for example, 1/10 of the length of the beam. All right, wonderful. That's great. So we have this. And then if you remember what I did before was in the previous exercise was I moved all the points on the top by a negative z vector that was multiplied by the depth. So therefore, I could create like a second collection of points, the bottom node for the beam. However, in this case, we will follow a similar approach, but we will need to do a little bit of pre-manipulation of the data. Because in this case, what we want to do is not really to take all the points, that are in the, we don't want to take all the points. What we want to do is we want to take only these points here. And those are the ones that we want to move all the way down here. So we're already going to have to do a little bit of data manipulation, which is going to be to take a subset of the points on the top, which is going to start with the second element, and it's going to go all the way until the second to last element. The way we're going to do that is as we learned on the previous videos when we talked about lists. There's a component that is called sublist, which extracts a subset from a list. And what we can do there is we can say that subset that we want to extract is going to be what? Let's think about this. So if we have our points and the points are labeled 0, 1, 2, 3, 4, 5, and 6, this is how the numbers are going to be labeled for a situation where n, the number of spans, equals 6. So what we need to do is we need to extract these points here. And the way we extract those points is by creating a domain where we say, can you give me, from the original list that goes from 0 to 6, can you give me elements that go from 1 to 5, or in parametric way, can you give me a subset that goes from 1 to however many spans do we have minus 1 unit? And therefore, those will be the elements that will be retrieved, and therefore we will create that sublist. Can we do that? I think we can do that. So let's take the list. We need to say what is the domain of indices to copy. So that's going to be, I'm going to create a new domain. I'm going to construct a domain here, and the domain is going to go from 1, which is always going to be the same, and that's why I'm hard coding it into a panel. I don't want a slider, because if somebody touches that slider, they're going to mess with my definition. And then B will have to be the amount of spans that we have minus 1. So what I can do is I can do either a tiny expression or I can do a subtraction. So I'm going to do a little expression because you know me already. I like this better and it looks more elegant, like x minus 1. It's easier to read. It's not so bulky. And then I'm going to take this here. I'm going to plug this in here. And you can see that now my domain is going from 1 to 5. Okay? So I'm going to move that here. I'm going to move that here. And then what I'm going to do is I'm going to plug all the points in here. And I'm going to see if these points are the ones that I want. You can see that as I turn them on, these points here, from the second to last, they light up. And if I modify the number of spans, everything is still parametrically, that looks good. So I think this is the sub-collection that I want to move to the bottom. So therefore, I'm going to use this here. And now I'm going to turn this on. And you can see that now I have the collection of points that are all the points from the top minus the first one and the last one. And then those copied on the bottom side. So great. So this is looking great. So, but as you saw on my previous video, because things are going to get a little complicated very soon, I want to make sure that I have a very clear sense of which points are which. So for the sake of clarity, before I start manipulating them, I'm going to, and this is really good practice to keep things tidy, so I'm going to just pass all these points through an empty point container box, and I'm going to label it. I'm going to say top nodes, and here I'm going to, in parentheses, I'm going to write all to make sure that we know that these are all the points. Then I'm going to write and not copy paste this one. And then I'm going to say top nodes. But here I'm going to write minus first and last. All right. And then the last is, this is going to be bottom nodes. And here I'm going to say all because I don't really need to differentiate between minus first and last. There was no such a thing here. Okay, so now I have here the result of my first processing, like source nodes. And this will be the one that I will use to start modifying and adding and removing, etc., to do the data matching, which is going to be, and I'm going to turn off the line here as well. And just for the sake of clarity and see things very clearly as well, this is very, very good practice when you're doing data matching operations. I'm going to keep here one of these components that gives me the numbers of elements on the screen. And what I'm going to do is I'm going to make sure these are all the nodes. Yes, these are all the nodes except for the first and the last. And these ones are all the ones in the bottom. So I think this is looking good so far. So I think we are ready now. We are in a pretty good position to now start looking at which kinds of which families of bars are we going to create and how we're going to match them together. Okay, so how are we going to do that? How are we going to do that? So I'm going to, okay. And then I'm also going to remove this. No, this. I want this. I don't want. I do want that. How did it get there? Huh. Okay. So, okay. Yes. All right. All right. So we have the points. Oh. So the numbers are. Okay. So I'm going to move the numbers to a new layer. And then I'm going to paste them. Okay. So these are the points. These are. Okay. So we're good. So where are we going to start? We're going to start with the vertical bars. We're going to start with the vertical bars, which are going to be these ones. And then that's going to be very easy because I already have this family of points here. I already have this family of points here. So that's one family, and I already have the other family of points, which is going to be this one here. So I think that's going to be very straightforward. So we can now just turn this off. Should I just move everything closer to the center? Can I do that? Can I just move all the layers? Well, I can do that next time. So these are going to stay here, I think. Okay. The first family of bars that we're going to create, I think is going to be the easiest one, the low-hanging fruit, which is going to be the vertical bars. And it's going to be the vertical bars because if you think about it, we already have a group of points that are all the top nodes, except for the first one and the last one, we already generated that collection before. And we also have another collection, which is basically all the nodes in the bottom. So if we match those one to one, we're going to get all the vertical bars right away. So it's going to be pretty straightforward. So that is just going to be as simple as, where are the top nodes minus the first and the last one? It's these ones. So, and then the other collection is this one here. So we're going to do simple line between two nodes. So that's going to be between the top and between the bottom nodes. And voila, we have all the vertical nodes. So that was pretty straightforward. And just because I really, really want to be very methodic about this, I'm going to turn this one off. And I'm going to write here vertical, I want caps. Where are my caps? Vertical bars. And that's going to be this one here. Okay, so we got this, and this is going to be vertical bars. Correct. So we got that. What are the next ones? Which are the next ones that we're going to do? And which one are the numbers? This one's here. Okay. The next family of bars that we're going to generate are going to be the top chords. And they're going to be the top chords because we already discussed in the previous video how, in order to do this, one of the easiest ways is going to be if we have a collection that is all the points, all the notes on the top of the bar, what we can do is we can generate two collections. We can generate a collection that is going to be all the points minus the last one. So those are going to be all the initial points of the lines. And then we can generate another list, which is going to be all the original top nodes minus the first one. And this all will be the end point of the bars. And then you can see how by doing that, it's very simple to see that if we join now with a line component element number 0 from the first list with element number 0 from the second list, we will get this bar. If we join element number 1 of the first list with element number 1 with the second list, we get this bar, and so on and so on and so on. We saw that on the previous video, and the way we're going to do this in this video is going to be slightly different, because what we did in the last one is that we took a subset. We took all the points, so all the top nodes, and then what we did was we created sublists that we splitted the list, starting with the first element and starting with the last element. So for this one, I'm going to follow a slightly different technique that is going to be a little faster, if you will, which is going to be shifting the lists. So let me show you how this looks. So right now I have all the points in my collection. So that's going to be this one here. And then what I would like to do is now, instead of splitting the list and just retrieving all the elements minus the first one and all the elements minus the last one, I'm going to shift the list. Shifting the list, if you remember, means offsetting all the elements. Okay? So what I'm going to do here is I'm going to take the list, and then the offset factor, for example, is going to be the value of 1. And by doing that, I'm going to end up with a collection of points, a collection of points that is going to be all the points except for the first one, which I actually still have it in my collection. So, and this is because if you remember from my previous video, I said that the wrap input, if it is set to true, it will take the last elements and then it will put it back at the beginning. So what I actually want to do in this case is to set that to false. So I'm actually going to write here on a panel false, and I'm going to set that here. And if I do that, then because elements don't wrap, as all the elements get shifted in the list, the one that was the last one cannot shift a position forward, so it just gets dropped. It basically disappears. So now I have a list that is shifted, and this will correspond to the collection that I have marked in red. So all the points on the top of the truss minus the first one. And then what I would like to do is I would like to make a very similar thing. So I'm going to copy paste this, and instead of 1, I'm going to type here -1. And then I'm going to now plot those. And you can see that because I also have wrapping deactivated, you can see that I have offset all the elements 1 position to the left, and therefore this point that was here moves here, and now the one that was in the first, it doesn't wrap, so it just disappears. So with this, so now I have the collection of points that are all the points minus the last, and I have another collection which is all the points minus the first. If I join this with a line between 2 points component, you can see that I will now have, let me just plug a panel here to make sure that things are working well. I have a list that is going to be, let me do 6 spans here so that it's a little easier. If it's 6 spans, I should be getting 6 lines there, correct? And I can see that I am getting 6 lines and each one of them has the exact same length. So that is correct. That sounds really good to me. Just to make sure that things are working well, again, what I'm going to do is I'm going to actually bake this result. So I'm going to bake this, I'm going to close Grasshopper, and you can see that I have what looks like a continuous line. But if I click on it, you can see that they're actually segments of lines one after the other, which is exactly the result that I want. So this is looking really good. So I think things are working fine so far. Remember, because I like things super tidy and clear, and this is really good practice, because trust me, Grasshopper definitions, they go nuts very soon with complexity. So I'm just going to make sure that I write here top chords, and I'm going to all caps that top chords. All right, beautiful. I'm going to wrap this into, no, I didn't want that here. So I'm going to wrap this here. So, oops. And I'm going to give it a name. So top chords. All right. And then for the ones on the bottom, I'm going to do the exact same process that I just did. But instead of drawing from the collection that had the top elements, I'm just going to draw from the other collection that had the bottom nodes. So literally, it's going to be as simple as just copy pasting this whole block here. All right. And then let me remove these 2 components from here. But instead of drawing from the top nodes, I'm going to draw from the bottom nodes. So I'm just going to plug this in here, and I'm going to plug this in here. And then you can see that the first list is going to be all the elements minus the last one. The second list is going to be all the elements minus the first one. And then when I join those with lines, I get these 4 lines, hopefully. Yes, 4 lines with equal length. All right. So, but then let me rename this because copy pasting is the devil, remember? So bottom chords, and here I'm going to write bottom chords. Beautiful. So again, remember shift list. What does is it offsets all the elements one position, but a byproduct of or a side effect of this operation is that if you set wrapping to false, all the elements that become empty with this repositioning disappear. They do not go back to the beginning of the list or they do not go back to the end of the list. And therefore, implicitly, it's a way of also removing elements from a list, which I find a little bit more elegant than the whole splitting ordeal. It's a little easier for me to read. I don't know. It's a different approach. So wonderful. So what is next? We just have to do the diagonals, right? How are we going to do that? Okay, so I am going to turn this off and off and off. And then I'm going to turn this on. No, these numbers here. I'm going to move this all the way here to the beginning, and then I'm also going to move this all the way to the beginning. Okay, and then so we have that. And then what we need to do now is in order to create the diagonals, we're going to do it in a 2-step process. So we're going to take these diagonals first. And then in order to do that, what I would like to do is I would like to take this, oops, no, nope. I would like to take this group. I would like to isolate this group first, and then I would like to isolate this other group. So for the first one, what is going to be the domain is going to be from 0 to the number of spans divided by 2 minus 1, for example. And for the blue, it can be the same. It's going to be the same. And divided by 2 minus 1. Okay, it can be the same, really. Mm-hmm. Okie dokie. Okay. All right. For the diagonals, as you can probably start imagining, we cannot actually do all the diagonals at once, because since we have two orientations, the left ones and the right ones, and they kind of have slightly different logics, we will just have to do two separate processes, one to fetch the ones on the left and another one to fetch one on the right. And you probably see where I'm going with this. If what I want to do is I want to take the diagonals that are on the left, what I will need to do is from all the lists of all the points that I have in my truss, I would need to do some list manipulation so that I isolate the first three nodes on all the top nodes, and then the first three ones on the bottom. All right, for in this particular case of a beam with 6 spans. So I will probably want to use some kind of operation where I extract a subdomain from the lists of original nodes. And what will be the logic here? So if I want to say, for example, I want to take from the top collection, what I would like to do is I would like to take all these points here. What that means is that I would need to create a domain that starts at 0 and that ends at 2. So that is for my extraction of those points. But 0 can be a hard-coded number because it's always going to be the beginning of the domain. But 2 has to be a parametric number, or a number that depends on how many spans do we have. And what do we think the rule is going to be? The rule for the number 2 based on a number of 6 spans could probably be something like this. We can see that the number 2 might be 6, the number of spans, divided by 2, and this can be hard-coded, minus the value of 1. Because this is 3, right? So we could write a rule where the domain that we choose to isolate the first elements that we're going to do for the diagonals could be something like this. The domain could be the value that goes from 0 to the number of spans divided by 2 minus 1. And this could be an inclusive domain that is typically done with brackets, okay? And then what about the other family, the family of blue points that I have in the diagram? How could we do that? The domain would be, for this case, it would be pretty much exactly the same, because we also want numbers that go from 0 to the number of spans divided by 2 minus 1. So the way we're going to do this is just going to be as easy as taking from the original collections, extracting subdomains that go from 0 to this parametric number, the number of spans divided by 2 minus 1. Let's take a look at how to do that. So we're going to go back to Grasshopper, and then we say, all right, we have all the points, all the nodes on the top, so all of them. So let me create a sublist here from all these top nodes, but let me before create a domain. So I'm going to construct a domain, and the domain is going to go, as I said, from 0, which is going to be a hard-coded number, and that's why I'm going to use a panel, because remember, I don't want a slider there. I don't want anybody by mistake to change that. And then B is going to be this parametric number, which is in relation to how many spans do we have. So obviously, you see where I'm going with this. I'm going to create an expression. I'm going to remove the first element, and I'm going to name this n, as in number of spans, for example. And this is going to be the number of spans divided by 2 minus 1. And I think the parentheses here are redundant. I don't think I need them, but I think they don't really hurt. It's just visual flavor. So I'm going to plug this in here, and the result for this one is going to be 2, which is great. And then I'm plugging this here, and then you can see that what I have isolated in this case are the first 3 points of the top list. And to make sure that this works, let me change the number of spans. And you can see that as we grow, we always get the first half, except for the point in the middle, which is great. So I think this is working pretty well. So at this point, I think we can take the points on the top. So are going to be these ones here. This is the domain. And the points in the bottom are going to be a sublist. So I'm going to copy and paste this with the same exact domain, but instead of drawing from all the types, all the points, all the nodes on the top, they're going to draw from all the nodes on the bottom. So I'm going to plug that in here. I'm going to visualize this. So I'm going to plug this in here, and these two look good here. And then I think at this point I can do line between 2 points, and ta-da! It works! Beautiful! And just making sure here. So I'm going to plug this in here, and I'm going to say left diagonals. Sorry. So I'm going to do left diagonals. So left diagonals here. And I'm going to group this, the diagonals left. Okie dokie. So I think we got this working. And if I increase the number of spans or not, everything looks to be working, right? Okay, so that is working well. Now, what about the other diagonals? Okay, so what about the other diagonals? So help me out here. So we will want to do this, can go, and then here. For this one, we're going to want to take a sublist here, and another one here, and then for that one, I'm going to do no. Oh yeah, because the angle. Oh, I cannot do the angle rotation. Okay. So that's going to be this one, and this one, and this one. And this is going to be 41 again. Okay. All right, so that's going to be 1, and then we have this, and then the domain rules are going to be a little more tricky here. So what can we do? For the domain, we can probably say that the domain here is going to be, oopsie. It's going to be probably something like n divided by 2 plus 1. This is going to go to n. So that can be one thing. And then the other could be the other could be, what could it be? What could it be? How could we do this in a way that makes sense? So I think this will always be n minus 2. So we have here n minus 2. And then this will always be half that, right? So n minus 2 divided by 2. Is that correct? Let's try that. I don't know. N minus 2 divided by 2 to n minus 2. Maybe that works. We'll see. I think that might work. So how am I going to explain that? That's going to be a good one. Okay. The right-hand side diagonals are going to need a tiny bit more of arithmetic, just like a little bit of more of adding and subtracting numbers. Because if you look at them, if you look at these diagonals, what you will see is that what we need to do is we need to extract the last half, more or less, of the points on each one of the collections, the one on the top and the ones on the bottom. And you're going to see that their index numbers are a little bit more all over the place. So let's take a look at, for example, what would be the rule for the points that are on the top. So you can see that the domain that we would need to construct here would be something like, for example, this would be the number of spans. So this can be n directly. And then this one here, as what we saw before, is that in order to find this one, what we did was we realized that this number was always going to be half of this one. So that's this one minus 1, correct? So this one was always going to be n minus 1. It was going to be n divided by 2, which is this one. And this one will be n divided by 2 minus 1. So I guess in this case, for this one, what we can do is that 4 is going to be n divided by 2 plus 1. Does this make sense? So the rule for the domain that we're going to create is that the first value is going to start at n divided by 2. That will be this number. Plus 1, so that will be this one. And then it's going to go to n, which is the number of spans that we have. Correct? So this is the parametric rule of the index numbers of these points here. So we're going to try that. And then the other one, how is the other one going to work? Well, let me undo this. Yes, so we have this one here. So what about, let me turn that off. So what about this domain here? So this is going to be also a little bit more arithmetic, because we know, for example, that this number here, which right now is 4, is kind of the last value of the list of all the elements in the bottom nodes. And because basically the bottom nodes are the same amount as the top ones minus the beginning and the end ones, if this value is always going to be n, turns out that this value will always be n minus 2. So if this is 6, this is 4. If this is 10, this is 8. If this is 3 million, then this is 3 million minus 2. Correct? So that relation holds, and therefore we can know that this number is also always going to be n minus 2. And then I think that geometrically, because the number of spans are even, it actually follows that this number, the one in the middle, will always be n minus 2, so this same value, divided by 2. It's always going to be the half of whatever this one is. So if that's the case, then I think we can make a rule here where we say that the domain for the points on the bottom is going to be n minus 2. So that's going to be this point here, and then n minus 2 divided by 2. So half of that is going to be that one here. And therefore, these are going to be both of our rules for designing the domains that we're going to use to extract points from the list of nodes on the top and the list of nodes on the bottom. Okay, so and I see Hania, who is live on the chat as I am recording this tutorial, is suggesting that another technique could be to do the exact same thing that we did for these ones, but before, what we do is we reverse the whole list. So we reverse the points on the top and the points on the bottom. So we reverse 2 lists, and we do the exact same technique that we used for the previous ones. That is also a technique that works. Perhaps it's a little less elegant or a little less clean because it involves reversing and then doing. It's so a little less straightforward, but it would also work. It would do the trick. And for such simple geometry, it's not going to be a big of an overhead. I like this approach better because it's a little cleaner, but also it gives me the opportunity to break down with you some of the numerical logics of how the points are sorted inside of this let me say that, please, inside of these lists of points. So I think it's good practice, okay? But yes, so reversing the list and using the same technique as before would also work. Nevertheless, let's take a look at how would we implement this approach. Yeah, you're right. Parisa, that is exactly what we're doing right now. I am explaining how to change the numbers, not really changing the numbers, but removing and working with the lists and reordering them around. Rolando, how are you doing, sir? Next natural step to avoid big, complex grasshopper definitions? I don't think we need to avoid them. What we need to do is, because sometimes the grasshopper definitions just get large and then they get complex. The only thing that we can do is just we can try to be very clean and very programmatic and group things and label things so that we always have an understanding of what groups of components are and we don't get lost on a large spaghetti of components. That can be difficult. So that's why you see me writing so many annotations and so much stuff, you know? So let's go back here. And then I'm going to disconnect this. I'm going to disconnect this. Parisa, as we... Oh my God, what did I do here? Whoa, whoa, that was bad. Yeah. What just happened here? Whoa. I think I copy pasted too much. Okie dokie. All right, so let's do this. So I'm going to go back to my definition, and then I'm going to use sublist to extract these two smaller collection of points from the original ones. So I'm going to sublist from the top nodes here, and I'm going to copy and paste another one, and I'm going to sublist from the bottom ones, and I'm going to take these two components and bring them all the way down here to work with them a little cleaner. So these would be the ones on the top, and these are going to be the ones in the bottom. Now, I need to construct a domain and now these are going to be different domains for each one of them. So for the one on the top, as we saw in the diagram, the rules are going to be that I'm going to use n divided by 2 plus 1. So what I'm going to do here is the beginning of the domain. I'm going to copy this, and the beginning of the domain is going to be n divided by 2 plus 1, as we saw on the diagram. Okay? And then the other end is going to be n, which means the amount of spans that we have. That is a parameter that we have in our definition. So I'm just going to draw here from this slider, which is the one that has the amount of spans that we have. So our domain is now from 5 to 8. And then if I plug this in here, you can see that I am getting the 4 elements that are by the end of the list. And you can see that if I expand, this is kind of working, it's doing what I expected, so that's great. And so that is working so far. And then I'm going to construct for the ones on the bottom another domain. All right, so I'm going to construct another domain. And as per the rules that we defined before, we said that the end of the domain is going to be the amount of spans minus 2. So I'm going to do that. I'm going to copy this expression here, and I'm going to say this is going to be the amount of spans divided by 2. That's going to be the end of the domain. And the beginning of the domain was that same value divided by 2. So I'm going to go back here, copy and paste this, and say n divided by 2. Sorry, n. Sorry, no. Oh, wait. I'm not doing this right. Sorry. It's n minus 2. And then n minus 2 divided by 2. Sorry. I was confusing myself. So I was a little confused. So this is n minus 2. Apologies for the confusion. And then this is why doing sketches is so good. And then this is going to be n minus 2. And all of this, and now I do actually need the parentheses for real, is going to be divided by 2. And this again is another one of the reasons why I like the expression component. Imagine having to do all of this and this and this with regular mathematic components. Is very tedious. It would have been a lot of visual clutter. So this should be the two domains, the domain and then the sublist, and then it just gives me these points here. And then I can just extract this and increase this, and I think this is working. And all right, are we ready for this? So let's do a line between 2 points, and then the first point is going to be the top ones, the second ones, and boom, and this is working. Yoo-hoo! And because I'm a little OCD, I'm going to do diagonals on the right, and then I'm going to group all of this, and I'm going to say this is the diagonals on the right, and boom. And I think I have my full truss working, right? So let me see. If I move the point, the whole thing becomes smaller. If I change the factor, the Pratt truss goes up and down. And if I change the amount of spans, I got more or less, or more or less. Yoo-hoo! Boom, boom, boom! It's working! Yay! All right. I think I want to try something. And if I fit this in here and in here, it kind of works. Wait, what? What? Oh, does this work or not? Divide curve. Oh yeah, I'm not. Yeah, it's not exactly working. Nah, it's not working. Ah, too bad. That would have been cool. Yeah, you see all these points here, there's some data problems here. So if we want to do this bigger, it requires like some other logics. Boom. That's unfortunate. All right. Well, I wonder. Wait, so what if we graphed? What if we graph this? Do we get? Ooh, actually that works. Okay. So I may just want to. I may want to talk about that. I may want to show that. Okay. Before we do anything else, something that I would like to remind all of us is that the nice thing about this parametric definition for a truss is that each one of the elements is individual. So what I can do is, and also for the sake of making things a little clean, I can create a final empty box. For example, a line empty box where I aggregate all together with the shift. I aggregate all the bars that I have generated, and this is kind of my main output. So this is like my my main, what is it called? This is kind of like my main my whole Pratt Truss. All right, and then what I can do is, like, for example, I can bake this, and let me say that I'm going to group it so that all the bars are grouped. So now I can close Grasshopper, and you can see that I have my truss that I could send it. I can actually move it around and send it anywhere to my structural analysis software. I can even ungroup it, and then as I ungroup, you can see that I can select all the individual members, including the top ones, which are in between nodes, and the bottom ones, which is kind of quite clean and quite nice. So this will be the main output of my definition. And just like I typically like having like a big box that says these are the inputs, I typically like having a big box that says this is the outputs. And sometimes what I even do personally is I bring it all the way here. And maybe what I do is, like, I right click and I say wire displays. I want hidden. I don't want to see anything unless I click. And this is my output. This is the main result of my definition, because at the end of the day, when people use definition, they should not care about what the code is. The only thing that they should care is about what are the inputs, what things do they touch, and what is the main result of an algorithmic parametric modeling process. So that's one thing. Another thing that I would like to highlight is, because now we have an algorithmic rule to generate these trusses, we can actually make it a little nicer and fancier, because since we start from 2 points, one at each end, and then everything that comes afterwards draws from that relation between those 2 points, then it turns out that it doesn't have to be just individual single points for support. Let me show you a trick. So for example, let's say that I had some kind of free form something, like for example, like a floor structure or whatever, and then I wanted to create like a series of parametric trusses between them. So for example, something like this. All right. What I can do is I can bring the 2 curves into, nope, not that one, the 2 curves into Grasshopper. So one here, and then I'm going to set the second one. It's going to be here. I'm going to subdivide each one of them in a set amount of points. So for example, that's going to be 20 subdivisions, if you will. And then I'm going to copy and paste this. And then here I have a collection of input points, and here I have a collection of output points. So if instead of using one single support and one end support, I use a collection of start supports and a collection of end supports, 2 lists, you can see that all of a sudden I get this parametric definition that generates Pratt beams between 2 collections of points. All right. However, if we look closely enough, let's reduce the number of these elements. If we look closely enough, we can see that there's something not right going on. So you see how these dimensions are not actually, and the more we add, we get some kind of strange curvature going on, but at the same time, we also get this collection of added points here. So something is not working very clean here. And as I typically say, when things are not working exactly the way we want, what do we think could be the problem? Well, of course, the problem is probably going to be related to data. I'm not going to get into the whys, but it turns out that that the problem is because we are outputting lists here of points. Those lists get messed up when down the stream we do list manipulation. So if instead of that, what we did was we grafted each one of the outputs, because now each of the points is in its own branch and it becomes its own list, then the problem gets solved. And now we get this parametric definition with trusses that are covering the span between the 2. And one of the beautiful things as well is that because we decided to do the depth, do it in a way that was proportional to how far off the nodes are, then the depths are not the same for each truss. They are different, and they are in a way a little more optimized. They're a little more optimized because you only need a smaller depths for the elements that are closer to each other. You can see how here the depth is very much, whereas here the depth is much smaller. So it's a very interesting way of creating parametric definitions. And it's a very interesting way of creating parametric structures. And I could add some pipes here and make it look a bit more nice, but it may take a little bit of time, and it's going to take some time, and it also is going to slow down my computer because representing pipes is actually quite expensive. So I'm not going to do that. So beautiful. So that was it. That was it. That was a parametric definition to create Pratt trusses between 2 supports or between 2 collections of supports. And I think that's it for this exercise. So just because I think lists are super, super, super important, I'm still going to do another exercise where we're going to do Warren trusses, which is also going to be very similar, but more list manipulation. If you think you're good with what you saw, you're welcome to skip to the next few exercises. Otherwise, I really, really recommend that you still check all the ones that are going to be related to lists, because lists are super important. List manipulation is super important, and it's always a topic that requires practice to get to wrap our heads around it if it's the first time that we're doing this kind of computational operations. So see you on the next video. This was Jose Luis. This was Introduction to Parametric Modeling. And if you are liking what you're seeing, maybe like this video, maybe subscribe to the channel, maybe turn on notifications, maybe leave a nice comment, or maybe just post some links to some work that you're doing from what you're learning on this list. That would be great. Thank you very much, and see you on the next video. All right, so now I need to record the introduction. Hello, this is Jose Luis, and welcome to another hands-on exercise in the series Introduction to Parametric Modeling. This one is going to be very similar as a continuation to the previous video where we did a Virendel Truss. In this one, we're going to do a Pratt Truss, which kind of looks something like that you're seeing here. And as well, we're going to work with 2 points that are going to be the beginning and the end of the supports, and we're going to be able to control how many spans the truss has and the factor of the depth in relation to the length. This exercise is going to be a little more involved because, as you can see, the relations between the nodes and how we join them with bars is going to be a little trickier. So it's going to involve a little more list manipulation. So we're going to learn a few tricks that are going to be super useful, and how to parameterize the relations between elements. We're going to do a lot of sketchboarding for that, actually. It's going to be great. And as a bonus, I'm actually going to show you how to extend this logic to work not just from 2 input nodes, but actually from a collection of input supports that come from a sample from a process of subdivision of 2 input curves. So that if we plug those into the definition, we can generate this parametric generative algorithmic modeling that just generates truss beams between 2 collections of points. And this could become the basis of some kind of like super empowered form of generating structures in 3D. I don't know. I think it's going to be really cool. So if you're interested, then let's get hands-on. Let's get dirty and do some parametric structures. Woohoo! Okie dokie. All right. So that was Pratt Trusses. Any questions? How did you like this? Was this good? Was it not good? You can be honest with me. If it's not good, you can just tell me. I will not take it personally. Mostly. And but it's also a good thing for me to learn when things are clear, when they're not, when they make sense. That helps me create better tutorials. So I'm going to take a small bathroom break and to get some water, and I'll be right back. And we're going to do now Warren trusses. And if we have time, which I think we will, we're going to do this really cool exercise where we're going to have a facade. We're going to triangulate the facade, and then we're going to take each one of the triangles and flip it and reorient it to the floor, as in to create, if you will, like the drawings of the dimensions of each panels in the facade, which is a very common operation to do in. It's a fairly common operation to do with parametric modeling. Okay, so give me a second. I'll be right back. All right. Woohoo. Okie dokie. Okay. All right. Ooh, I'm a little tired here. Now, war and beam. How are we going to do that, actually? Let me think. I have... Oh, how's everyone doing? How are you holding on? Huh? Where are we? Uh, uh, uh. Mm, okay, and then... Oh, I see. Mm-hmm. Oh, this is going to be cool. Should we do this instead? Hmm. Huh. I'm having an idea to do like a... Instead of a simple war and beam, which is kind of boring, we can do... let's do, for example, what if we did something a bit more special, a bit more designy, if you will. So let's do something a bit more designy. So let's do something like airport roof truss. I think, yeah, I want to do something like this. This could be cool, or something like this. This is also a cool example. Oh, what is this? Ah, this is the Mumbai airport, isn't it? Something like this or like this. What about this? That could work, I guess. Which airport is this, by the way? I don't even know which airport is this. Um, mhm. Hmm. Hmm. Should we do something like this? Or should we just do like a simple war and beam? It's going to be kind of tricky. Uh, hmm. Let me think about that for a second. So I guess I'm whether if I'm thinking of whether if to do this. I guess I'm thinking whether if to do this exercise here, so a simply supported Warren Truss like the ones that we have seen before, or to do it more spatial like these ones. So take like some geometry, generate like the 3 bars, and then start doing subdivisions and figuring out the points. Huh. I am not sure of what to do. Not very sure. So what do you want? Let's vote. So do you want the spatial one, so this one, the airport one, or do you want the plain flat one, the Warren Truss? What do you think? Rolando wants the spatial one. Okay, I'm happy to hear votes in favor, votes against, whatever you think. Give me some opinions. The spatial will take more time. It will be a longer exercise. The Warren will definitely be a simpler one. This will be a simpler one. So what do we want? Do we want? I guess we want cool, right? We want something cool. Probably. Correct? Hey, Flora, it's been a while. Good to see you. So we have 2 votes for spatial. Any vote for plain truss one? Anyone has an opinion? Okay, well, I guess we're doing spatial then. Well, that is going to take some time then to figure out. Okay, so, well, we can do that. Yes, we can do that. So let me just write here my notes. Afternoon of 26.5. Okay, so it's going to be a little. Oh God, another spatial vote. Okay, fine. We will do the spatial one. Okay. So, all right. Space frame. Okay, so so it looks like everybody wants to do a spatial frame. So, all right, hold on to your seats because it's going to be quite a ride. Okay. Okie dokie. So, how are we going to do this? We're going to do, I'm going to start with some sketching, and then in the sketching, I will explain which parameters I am going to control. And I will explain first that I'm going to do the 3 main curves, the 3 main axis curves, and we will draw those parametrically. And then once we have that, we start taking a look at how to do the Warren kind of distribution. Okay. All right. Give me a second. I need to do something. I'll be right back. I'll be just 1 minute. I'll be right back. All right, let's do this. Woohoo! Now let's do some sketching then. So we are going to save this, and I'm going to start a new sketch. And for the new sketch, we're going to do the following. We're going to start by with a no, what just happened? Oh, can you see this? Oh no. I think yes, I disconnected. My sketching disconnected, sorry. Why is this happening? Okay, so sorry, I need to rearrange. It was working so well. And okay. All right, so let's go back. So we're going to start with two supports. One support here, another support here. So we're going to start with those two supports. And then what we're going to do is we're going to draw one bottom curve like this. Okay, that's going to be one. And then we're going to draw, oh no, again? Sorry, but for some reason it keeps disconnecting. So that's going to be one. Then we're going to have the other two, which are going to be something like this, and another something like this. Wow, that was a really shitty diagram. Something like that. Oh. Forming here a triangle. Forming here a triangle. We're going to be forming here a triangle, and this triangle is going to look something like this. All right. And then things that we will want to control will be this length. So that's going to be the length. And then probably we want to control as well. We want to control this height here. This height here. We probably also want to control the depth and the width. So the depth and the width, something like that. And then what else? And probably all of these will be done as factors. As factors of the length. Factors of the length. And then once we have that, we can probably just start doing the triangulation. So that's how we're going to start. Wonderful. So let's get started. How are we going to approach this? Well, as we saw on the diagram, we're going to create these spatial structures that are going to be spanning a very large distance on top of two supports. And they're going to have basically a kind of triangular section of sorts. And they're going to have a triangulation of bars that is going to be following more or less that Warren logic that we spoke of. So what we're going to do is, I think we're going to divide this exercise in two main parts. The first one is going to be creating the basic geometry, so creating the two supports and then creating the three main bars, like long bars that join them, the triangulated section. And then a second stage will be creating the internal triangulation inside of the truss to give it stiffness, to give it stability. And And for the first one, and for the first stage, we're actually going to do it a little faster because it's like basic simple geometry manipulations and things that we are already a little familiar at this point in this playlist. So we're going to do a simple process where we're going to start with two supports, which are probably going to be points in Rhino because we like the fluidity of moving things in Rhino, etc. Then we're going to create some kind of nerves curves that is going to join them like that. And then we're going to create another two nerves curves on top of it, which in a way somehow are going to create this triangular section among them. And then probably the parameters that I will want to control here are going to be the following. I will probably want to control the length of between the spans, which is not going to be direct. It's going to be, as we said, implicit based on where the 2 points are. Then we probably want to control the base height of the arch, so the main opening that is going to the main height of the arch, right? We will want to control small things such as the depth and the width of the triangulation at the center of the beam. And for these three elements, for the height, for the depth, and for the width, I think I will want them, except maybe the width, I'm not sure about that. I will want to, instead of having them as straight values, I would like to have them as factors of the length, so that whenever the length is smaller, the height is smaller, and also the depth of the beam is smaller as well. So that we get a more optimized beam, a more optimized truss, as we saw on the previous exercises. So I think I'm going to go ahead and do this, and perhaps I'm going to do it a little faster than usual so that we can get this done as soon as possible, and then we can start dealing with the more complicated part, perhaps, which is going to be designing the internal triangulation of bars that is going to be inside of the truss. Let's get started with this. Let's boogie, maestro. I like that. Okay. All right, so I'm going to go here. I'm going to go, okay, so I need to start. So that's going to be, and then I'm going to save this as E17 Warren spatial Truss. And then this is going to be the Pratt Truss is going to be wait, so I'm going to save this also as the 16 in case I'm going to save this and I'm going to save this as 17. Okay, yes. And then here I'm going to save this as the and this is going to be optional curve inputs. Connect. Disconnect. Okay. So that is going to be the Pratt Press, and then just going to create a new. And then I'm just going to create a point here. Actually, let me open that. Let me just. Okay, and this one is linked. Okay. So. So start support, end support, and then what else am I going to do? So I'm going to do the height as a factor. So I'm going to do, and slider type is going to be, there's going to be 30. I'm going to open this up, and this is going to be height as in SL divided by L divided by this value. L divided by this. What am I doing here? L divided by this value. Okay, that's the height. And then the depth. Truss depth. Truss height. Truss depth is going to be L divided by 30, and truss width is going to be L divided. Height is going to be L divided by 2. I don't know if that's going to work. Height should be, what should it be? Should be like L divided by 2. So for example, half. Depth should be divided by 12, and width should be divided maybe by, I don't know, 18 or something like that. I'm not sure about that. So I'm going to, these are going to be my inputs, mostly correct. Those are going to be my inputs, and those are going to be as factors as L. And then what am I going to do after this? So I'm going to create a line. I'm going to find the middle point. I'm going to move that in C an amount that is going to be equal to H. And then I'm going to create another point and I'm going to move. And then I'm going to move perpendicularly. How are we going to do that? So we can create a plane between the 3 points, and then we can find the normal, and then move the point normal and normal. So that can be a process. That we can do that. That's interesting. Plane between 3 points, the normal, then we move those points, and then we create the 3 main arches. So that's what we're going to do. Yes. Okay. Beautiful day today here in Cambridge. I'm so gonna go for a run today. It's gonna be amazing. Woo-hoo-hoo. It's gonna be definitely a 5K, maybe a 7 or 8K day today. That could be nice. Woo-hoo. Do any of you run? I think many of you do run, right? I see that on your introductions on Discord. Okay, so let's get started. Okay, to speed things up, I have gone ahead and started the Grasshopper definition as usual. I have 2 points in Rhino that I brought here as empty boxes in Grasshopper, and I have a few sliders that I have customized to be the height of the beam. And look at what I'm doing here. I am just annotating myself here that this height is not going to be an absolute value in units. It's going to be whatever the length between those 2 points will be divided by this number. This is just my internal annotation. And same for the depth. The depth will be whatever the length of between the 2 supports divided by this number, and the width will be L divided by this number. So the 3 factors are going to be factors of the length. And then what I'm going to do is I now need to create the 3 main arches. I'm going to follow a very simple logic, which is going to be if I am here, so my logic is going to be that I'm going to create, I have the 2 supports, I'm going to create a line between them, find the point in the middle, I'm going to move that point like a controlled amount of distance in the z direction, which is going to be h, and then that point, I will move it up a controlled distance here, which is going to be the depth, and I will move it in the 2 directions, like half the width and half the width, so that I can create the 2 points here, so that I can create an arch between these 3 points, another arch between these 3 points, and another arch between these 3 points. And those are going to be the 3 main arches that I will use in the rest of the definition for calculating all the bars and all the structure inside of the truss. So let's get started. So very simple. I'm going to group this because these are my inputs, and then I'm going to create a line between 2 points, a bit between the start point and the end point, and then I would like to find a point at the center of that line. So what I can do is I can go to curve analysis, and I can find, for example, I can evaluate the curve. What is evaluate the curve? I can evaluate the curve so that I can find at a specified parameter, I can specify points, tangents, and angle. Because I know that a line, by definition, has a domain that goes from 0 to 1. I know that the center point will be exactly at the parameter 0.5. This rule only works for straight line segments. It doesn't work like this for curves, okay? Remember that, please. And now we have evaluate curve. So this is the point, and then I just need to move that point in the z direction. I just need to move that point in the z direction, a control amount that is going to be equal to the height. But the height is a factor of the length between the 2 points. So remember that I need to take this and I need to calculate the length between the 2 points. So that's going to be the length of this segment. All right. Or alternatively, I could also do this. We haven't seen this yet. I could also do this by calculating the distance between 2 points. So if I go to vector, point, and distance, you can see that here I can compute the Euclidean distance between 2 point coordinates. And that is going to be the starting point and the end point. And that will give me d, which is a linear distance between them. If I now divide that distance division by the truss height, this will give me the actual height of the truss. And actually, sorry, I'm going to just move things around a little bit, and I'm going to add myself a number here. Sorry, this is not a number. I'm going to add myself a number here to remind me that this is the actual height, not the factor, but the actual numerical height that I will probably be using along a lot farther down the road. So I would like to now copy and paste this 3 times because the depth will be a factor of this and the width will also be a factor of this. And so this will be the depth, this will be the depth, and this will be the width of the beam. And I'm going to group this as in these are the actual calculations for the height, the depth, and the truss of the beam. So that I have them, the 3 numbers here, and that I know where to drag from as far as as much as I continue developing my definition. So as I was saying, I have my point here. I want to move it up. I control amount z, and which is going to be equal to the height, this value that I've already computed. So I plug that in here, and then I can now create, for example, an interpolated curve, which is going to go from the start point, the start support, to this point in the middle that I generated. So I plug in by pressing shift so that they both go in together. And then the third point is going to be the end point. So I also shift add it here. Correct? And this is going to be the main, this is going to be the base arch of my truss, which is going to be somewhere here. And if I want to name this, I can drop an empty curve box. This is going to be the base arch, and I can click on the paint bucket to give it the name here. Okay, wonderful. So this is how we do the base arch. So now let's do the other 2 additional arches. All right, so what just happened? Something cracked. My light just cracked? Well, that was very strange. I'm safe, everyone, don't worry. All right. If you remember from our diagrams, well, the only thing we need to do is we need to take the base point, which is here, and we need to move it up and to the left and up and to the right, controlled distances, which are the depth of the truss and half the width on each direction. So let's see how can we do that. So we're going to, we have the point here. This is the point on top of the arch. So we're going to first figure out how to move it in the z direction. The z direction is going to be just as simple as taking another z vector that is factor or multiplied by the depth in the vertical direction. And then we can take, for example, we can take this point, the point that we did, and we can just move it up by that factor, and we just have it there, right? Now, what we need to do now is we need to move this point in half the width in one direction and half the width in the other direction. However, technically speaking, we don't really have anywhere, we don't really have a vector that is pointing perpendicular to the plane that is formed by the starting support, the middle point in the arch, and the end support. We don't really have that vector anywhere. So there are 2 ways that we can go about this. We can either create a vector in this direction and then take that vector and rotate it around z 90 degrees. That can be one way to go, but I'm not sure that I like that one a lot. I think I like better to just say, why don't we create a plane that is containing this point, and this point. So something like this, a plane that is, the origin is here, the main vector is pointing in the direction of the other support, and we use the third point to take the second to define the secondary axis. And then what that will give us is a plane whose normal, the normal vector, is going to be perpendicular to that arch. And therefore, if we use those 3 points, then we know that that vector will always be perpendicular no matter of where the 3 points are in 3D space, which is something that the previous technique may not address very well. So I think we're going to do that. So we're going to do that, and we're going to say, let me create a plane defined by 3 points. So I'm going to go to vector, plane, and I'm going to create a plane defined by 3 points. Which are those 3 points going to be? The first one is going to be the starting point. So that's going to be the start support here. The second one is going to be pointing to this point here, which is the second of support. So that's going to be the end support. And then the third point is going to be a point that is going to be the one that we just defined before. And therefore, look how nice this is. We have a plane now that is centered here, that is oriented towards the other support, and whose secondary axis is pointing upwards and is containing the arch, which is a planar curve. The normal to this plane will be a vector that is perpendicular to this plane. So let me extract that normal by deconstructing the plane and, for example, visualizing that vector with a vector display. So I'm going to visualize the vector here, and the vector that I want to visualize is this one here. So you see, this vector is now pointing outwards from the plane of the truss. So if I now take that vector and set its length to be half the width, then I can multiply that by 1 or by -1, and that can be the vector that I use to move this point in this direction and this direction. So let's do that. So I'm going to calculate here. On one end, I'm going to calculate with an expression. I'm going to type, this is going to be W, and then what I want to calculate here is W divided by 2, that's going to be 1, and then the other one is going to be minus W divided by 2. And then, because I have the width here, I'm going to plug these two here, 1 and 2. And then I'm going to multiply the normal vector C. I'm going to multiply it by this expression. So I'm going to multiply it by this length. And I'm also going to multiply it by this other length. And I'm going to visualize that here. I'm going to visualize it here. That's one. And then that's also the other one. But if I want to visualize them on top here, I can also visualize them there. All right. And then, just like I have added, what I can do is I can add the C vector with the depth and the C vector with the width. I can add them together to create, for example, let me add the vector that is going to move this point up. Let me add that vector to the vector that is moving it in the left direction. If I now showcase that vector, you can see that it's a vector that is pointing sideways out of the plane. And if I now do the same with the other vector here, you can see that as I add it here, I have the two vectors that are moving this point in the triangular form. And then as I do that, I can just move the original point by this vector, and now move the original point by the other vector. And I can turn this off, and I can see that I now have the three main points for each one of the arches. And then what I can do now is I can say, well, this is going to be one thing, and then this is going to be the main arch, and this is going to be here. I can copy and say, I'm going to create an interpolated curve. I'm going to disconnect everything. just to make sure that I do it right, between the start point, the new middle point I have created with a shift, and the end point, the end support. And then I'm going to create another interpolated curve. I'm going to copy and paste. I'm going to right click here and disconnect everything. And then I'm going to plug in the first support. I'm going to plug in the middle point with the shift. And then I'm going to plug in the end support. And you can see that I have the 3 arches, each one of them with the base one, and then the 2 on the top with the opening. And if I control things here, you can see that this is now adapting. This is also, the depth is also adapting, and the width is also adapting. And it also adapts because if I bring the points closer to each other, everything opens up proportionally. So I'm going to now turn off a bunch of geometry that is kind of temporary, like this one and this one and this one. And I'm going to make sure that I end up with the clean 3 boxes. Top left, for example, top left arch. And this is going to be top right arch. And I'm going to move them here, and I'm going to create a group to make sure that they are very clearly identifiable. I'm going to turn off the plane as well, and then this middle point here. And now, very cleanly, I have those 3 curves, those 3 arches that are joining the 2 support points. And all of this, I can probably now just create a group here, and then create another group here, and then I would label this, blah, blah, blah. But I know that anything that is happening here in the middle, I don't need to care about anymore, because what's important is that I have been able to generate those 3 curves, the base, the top left, and the top right. Okay? So at this point, I think I'm ready now to start working on creating the triangulation inside of the truss. Let's take a look at how to do that. All right. Okay, so how are you holding on? How is everyone holding on? Are we good? Are we getting this? Is this too fast, too slow? Let me know how are you feeling about this, please. And then and then let's go back to the drawing board. I think I'm just going to save this one and start a new one, because how am I going to explain this? Thank you, Flora. Oh, the lights are off. I think that's why the thing just, yeah, that cannot be right. Something just broke inside of this thing. Huh. Okay. Okay. How am I going to explain this? So basically, between us, and then I will figure out how to tell the story in a more formal way. So basically what we're going to do is we have the arches, okay? And then what we're going to do is we're going to subdivide them into segments. Okay, and then this and this and this and this and this. But the first thing that we're going to do is we're going to remove this and this because we don't want to start triangulation here. So we want to start triangulation something like this, for example, something like that. So I can say that. So that's one thing I can say. Thank you, Parastorm. How are you doing? It's been a while. Good to see you. Then we're going to take those and then Are we going to force these ones to be even? So maybe we could do it. So the number of gaps here is going to be equal to 4. So we need to add 4 more, and then we will need to remove those. And then after that, we will need to weave this into a list that has this element, this element, this element, this element, and this element. For example. And how are we going to weave these? How are we going to weave these? With weaving, literally. Okay. All right, so let me actually draw a diagram that is not this stuff here. Okay, actually this stuff doesn't look that bad, but regardless, we're going to draw it nice. So I'm going to the support, that's going to be one support, that's going to be the other support, and then this is going to go out. Oh no, the support is behind my head. Nope, we need support here and another support here. Oops. Okay, so that's one thing. Another thing. Now, so that we're going to have I'm going to exaggerate the shape so that we, that was a terrible arch, oh my god. So that we have room for, oh my god, that was terrible. Please, please don't look while I'm doing this. You see, the faster I do it, yeah, I like that. Okay. So first we need to decide we need to divide into a control amount of points. So for the bottom curve, that's going to be, for example, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And for the top one, it's going to be similar. Then the problem is going to be that we cannot really do kind of like that. It looks weird. So what we will want is instead to just create something that looks like this, and we leave some room there. So we will need to either we'll need to fetch these ones here and either these ones here or these ones here. And then after we do that, how is it going to be? So we're going to end up with a list of points that are going to be 0, 1, 2, 3, and 4. And then another list that is going to be 0, 1, 2, 3, and 4. We could do 2 families, but at this point, because I want to teach something a bit more elegant, what I would like to do is I would like to teach people to create a polyline between point 0, point 1, point 2, point 3, and point 4. Okay. A polyline between this one, oopsie, polyline between this one and this one and this one, and a polyline between this one and this one. And therefore, hey Matthew! Wow, good to see you. Long time no see, man. It's a pleasure. Matthew is an old friend from the Boston community, from the GSD Harvard community as well, and he's been doing a lot of really cool work on computational design as well. And we used to kind of teach together at the GSD, more or less. Good to see you, man. What is up? What is life? Tell us a little bit of what's going on. Are you still here in Boston? All right. And then the way we are going to do this is by weaving and by culling and we're going to use a process that is going to be called culling plus weaving. That's what we're going to do. Okay, so let's see if I can tell the story now. So okay, so oh, I need to start from scratch, right? Oh yeah, I have nothing. Yes, okay. So let's get started. Oh, and I need to explain that I'm going to be dividing and that I will then be, whatever n is, has to be n plus 4. Or I can define that as S gaps. Huh. Okay. Okay. Let me think through this. All right. So okay. So let's get started. As usual, thinking by drawing or by sketching is, I think, is one of the most useful ways of thinking through problems. So let me explain how I think we're going to approach this problem. What we have is an arch that is the base of the truss, and we have two other curves that are the top of the arch. And for the sake of this diagram, we're going to assume that the top one is the same. It's just the two. We're not going to take care of that. And then what we're going to do is, in order to start generating bars that generate the internal triangulation of the truss, we probably want to do something where we subdivide each one of the curves in a regular amount of points, in a controlled amount of spans, right? But then, if we just took all of those points and we started joining them with bars, the way we've done in previous exercises, because of this particular truss in 3D space, because it kind of has this shape that starts as in one point and then it opens up and then it closes down, if we were to just generate triangulations like that, we would probably end up with something like this, where I'm not sure if you can see, but here on the ends, these bars look kind of weird. And if this opening is not big enough, these bars may also be kind of like they're like a little bit in the way. So it's actually very common that in these kind of special structures, there is like a gap, typically a large gap here before you start actually doing the triangulation. So I would like to propose that we also do that, which is just involves a little bit of data manipulation. And if we say, for example, that if we said that this, for example, if we said that this truss needs to have, for example, 8 spans or 8 gaps between them, which is the total amount, we may also want to define another variable that is going to be, for example, the number of void gaps or void spans at the ends of the truss, which in this case, for this diagram that I'm drawing, could be 2, so that I have 1 and 2 spans that are empty, they don't have triangulation, and then I have another 2 spans that don't have triangulation, but the total is 1, 2, 3, 4, 5, 5, 6, 7, and 8. Okay? So what we will do is we will calculate the total amount of spans, but then we will subtract, we will remove only, we will remove points at the ends of those collections so that we only do triangulations at the center. Now, something that we probably will want to do after that is extract from those two collections the points that I'm going to do triangulations on. And again, this will involve figuring out how many gaps, how many empty gaps do I have on the sides. And also something that I could do is I could arguably say I'm just going to take these two collections, or because I know that the triangulation is in a worn way, I may want to just take the one here in the bottom. Maybe, I don't know, without the other one. So I think that for symmetry and also for showing a little bit of the other techniques that I want to teach you, in this case, in this particular exercise, we're going to take the same amount of points from the top and from the bottom arches. But arguably, you could decide to just design this algorithm in a different way. It's not a bad thing. And then after we have that, what we will end up with is with a subset of points that are ordered in this particular way. So the top points and the bottom points. I could use techniques similar to the techniques that I have used in the previous exercises. What I now can go and say, well, I want to now draw this bar and this bar, all the ones that are to the left, and then on a separate process, I'm going to do the ones that are to the right and to the right. This could be a way to go. But since we've already learned how to do that, I kind of want to teach you different techniques now. So what I would like to propose is that for this particular exercise, we follow a different technique. And the different technique is that since this exercise is maybe not so much designed for structural calculation, but is more for the design of an airport canopy or whatever, in this case, what I would like to propose is that instead of generating individual bars, what we do is we create one continuous polyline between all those points, that we generate a continuous polyline between these points, between the first point here, the second point here, the third point here, fourth point, and the fifth point. And then if we need to explode that polyline into individual segments, we can do it at a second process, but the result will be a polyline that will do something like that. So for that, we will actually need to do some kind of geometry processing or list processing that will involve creating a new line that has element number 0 from the top, element number 1 from the bottom, element number 2 from the top, element number 3 from the bottom, element number 4 from the top. And that process is going to involve doing two operations that we haven't seen on the lectures, but that I will teach you through this exercise, which are going to be culling. So that will involve removing this element and this element from the top one, and this element and this element and this element from the bottom one. So cherry picking how to remove elements with a pattern, and then weaving, which will be creating a list that instead of having all these elements and then all these elements afterwards, which is what we know how to do now, we'll have this element weaved with this second one, weaved with this third one, fourth one, in this particular arrangement that I have defined here. Are you excited and ready to do this? I think it's about time that we give it a try. Let's take a look at how to do this in Grasshopper. Oh, Matthew, you left Boston? Boo, boo. Well, I'm very happy to hear that if you're doing well in San Francisco, I'm very happy to hear about that. But yeah, let's catch up sometime, anytime. Okie So back to Grasshopper. Okay. I'm going to add here the number of spans, and this is going to be even. And that's going to be 1, and then that's going to be 2, for example. And this one doesn't need to be. This one doesn't need to be even. Okay. Okay. So what do we do next? The next thing we're going to do is we need to do the subdivisions for each one of the curves. Mm-hmm. Okay, so I'm going to do that. So I'm going to do here, base arch, top left arch, and then I'm going to extract. I'm going to figure out, I need to extract that, so the subdomain is going to be what the subdomain is going to be, and then we need to call the elements. Okay. So back in Grasshopper, I have created two sliders. One is the total amount of spans, as we discussed in the diagram, and the other one is going to be the number of void spans that we're going to have on each side of the truss. And I will use those numbers to do my data manipulation, my data list manipulation. So what are we going to do now? So what I'm going to do is I'm going to take the base arch and I'm going to divide into a bunch of spans. Okay, how many segments am I going to divide it? The amount of spans that I have defined here on the number of spans that I have defined on my inputs. So that's going to look something like that. And I'm going to do the same thing for the top left arch. And just to keep things a little clean, I'm going to kind of forget about the other one for the time being. So, because the other one is basically going to be copy pasted from the left one. So I'm just going to work with one of the ones above. So what I need to do now is I have all these points, so all the points in the bottom and all the points in the top. And what I need to do is I need to extract the families that are going to be at the center after I remove the the gaps on each side. So what I need to do is, if I'm about to do this in a clean way, the way to do about that is by defining here, extracting from the list of curves just a subset of extracting just a subset of those points. What is the domain that I need to extract going to be? And the domain is going to be, let me try this real quick, and then we take a look at that on the whiteboard. So the beginning is going to be the number of spans, and the total is going to be the number of spans minus this one. Is that correct? The number of spans minus this one. I think not sure. Oh, yep, that actually worked. Okay, so then let's go to the diagram here. So where did I annotate? Here. Okay, doesn't matter, so I'll just throw it again. So if I said that, oh no, not that brush. If I said that the amount of gaps is 8 and the amount of voids is 2, we said 0, 1, 2, 3, 4, 5, 6, 7, and 8. And that if I want to take these elements, then say if I want to take these elements, actually I can draw that. You know me already. I like thinking through drawing, so let's take a closer look. So if we imagine that we have a situation where the number of spans is 8 and the number of voids on each side is 2. So what we would want to do is we would want to extract this family of points from that list. And if the points are numbered like this from 0 to 8, because there's 9 points, remember there's 8 spans, so that means there's 9 points. So what I probably want to do is I want to create a domain where I extract from this element, whatever its index number is, to this element, whatever its index number is. And it turns out that the first one, this one, is going to be equal to V, to the amount of spans that we have on each side, the amount of empty ones. And it turns out that this one here, the last one, is going to be equal to the amount of total spans minus the amount of empty spans on each side. So if you see here, 6 is going to be equal to 8 minus 2, correct? So it's going to be a very simple numerical rule about creating the domain that we're going to use to extract this sub list of points from the total on the top arch, and the same for the bottom arch. So let's just do that. I'm going to click here and I'm going to construct a domain, and then I'm going to move the sublist here, and then the start of the domain is going to be equal to this parameter, so how many void spans, so that's going to be the number 2. So that's going to be the start, and the end, as we said in the diagram, is going to be the amount of spans minus the amount of void spans. So that is going to be super easy. So I'm just going to create a subtraction here. I'm going to subtract from the total amount of spans. I'm going to subtract the amount of void spans. And that is what I'm going to use for this end of the domain. If I do that, if I plug that domain in here, you can see that when I click, this point turn on, and let me see if this works. So if I add many more spans, yes, it is true that there's always 2 empty ones here, but if I increase this, you can see how I start getting more empty spans on each side. So I think this is working correctly so far. So we are going to use that for creating the sublist also from the points on the top arch. So that's going to be the points, and this is going to be the same domain. Okay, and I'm going to turn this off, and then you can see how now we are left with the points in the bottom and the points in the top. And as I typically do, because we're going to start getting, it's going to start getting messy with lists and combinations, whatever, I would like to have the point list component here nearby to make sure that I have a good control over what's going on. Okay? All right, so what is next? Was I recording my screen? So, did you see me using Grasshopper right now, or was I just on the sketch altogether? So, did you see me right now sublisting and constructing the domain, or was I all the time on the sketch? Do I have to re-record this again? Did I mess up? Can someone help me here? I can't go back on the video and see myself. Did you see me? Did you see me like putting together these components and like extracting these points. Yo mama, yes, you saw that. So I was on this screen right now, right? Okay, cool. Sorry, I freaked out for a second. Okay, thank you. Hey, Hex, how are you doing, sir? It's been a while. Good to see you. All right, so now, what are we doing here? So how am I explaining this? I'm explaining calling. So I want to explain that I have the whole list. All right. If we go back to the diagram, what we need to do now is from each one of the families of points, the top and the bottom. So from this one, we need to basically remove every other point from the list. So from this one, I basically want to remove this one, and keep this one, and keep this one, and keep this one. And from the bottom one, I want to remove this one, and this one, and just keep this one and this one. So I need to take the two lists that I just generated and use a process called calling to apply a pattern of yes and no to which points do I want to keep and which points do I want to remove from that list. With the techniques that we have seen so far, there aren't any operations that do this on the list. So let me show you a component that we can use to do that. That component is going to be here under sequences, and what we can do is, for example, we can call or we can remove elements in a list by using a mask, by using a pattern. What does that look like? So I'm going to plug my points here. I'm going to work on the ones on the bottom, and you can see that the call pattern component takes the list that you want to call and then a pattern, which is a list of trues and falses. A list of trues and falses about which points get to stay and which points get to go. So how is that going to work? Well, you can see that the pattern list already has a default, which is false, false, and true, true. And that if I apply that here and I visualize these points now, you can see that false, false, left, true, true, stayed, false, false, left, true, stayed, and then etc. etc. So true means the points are going to stay, false means that the points are going to go. So what I need to do now is I need to create myself the pattern that I want for my calling. So as you can see here, it's in blocks of 2. In my case, it was for the bottom one, it was blocks of 1. So I want 1 out, 1 in, 1 out, 1 in, 1 false, 1 true, 1 false, 1 true. So I'm going to do this. I'm going to write here a panel, and then in the panel, I'm going to double click and I'm going to write false so that the first element goes, and then I'm going to type here true so that the second element stays. And that is going to be enough because this pattern is going to repeat over and over. When I plug this in here, I don't think it's going to work because since I have 2 lines in my panel, I need to make sure that the component knows that it's 2 different lines. That is basically a list of inputs. So the way I do that is by right-clicking here and making sure that this is not multi-line data, that is single-line data. And you can see how the panel immediately turns into a tiny list with a branch and zeros and ones, and now it's a collection of elements. I could add more here and blah, 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 but if I do that, it's going to give me an error, obviously. So I'm just going to double-click and remove all those lines. All right? And I'm also using a panel because I want to make sure that no one changes this. For me, it's important that this pattern has to be like this. So you can see how I had these points, and now after calling the list, what I have is only this point, and this point, which kind of matches what I wanted to do in my diagram. So I'm going to use the same technique to call the points that are on the top. All right, so I'm going to copy and paste this, and I'm going to plug the other list. However, and then I'm going to turn these points off. However, if I do that, you can see that I'm going to be calling the same points, and that if I look at them, I have the same ones. I don't have the triangulation that I want. And this is because for the other arcs, I need to actually change the sequence, and instead of starting in false, I need to start with true and vice versa. So this needs to go, and this needs to be here. And if I do that, you can see that now, if I turn this off, now I have been able to keep in the bottom these points, in the top the opposite ones, correct? And then, thankfully, I should be able to take a polyline and then just do, can I do a polyline between all these points and all these points here? But as you can see, it's not working. And it's not working. Why is it not working? When things are not working, what do we think is the most probable cause? It's probably a data problem. So as I typically suggest, can we first use a panel to take a look at what's happening here? If I take a look at this panel, I use this panel to see these are the first points, these are the ones on the bottom, these are the ones on the top, and then I'm going to create another panel where I'm going to replicate what is happening here. So I'm going to plug in the first one, and I'm going to shift add the other one. And you can see that what's happening is that the 4 points are added to the end of the list. And therefore, the polyline goes first through the 3 points on the bottom. So 1, 2, 3, you see that here. And then the polyline continues over the 4 points on the top. So polyline goes here and then continues the 1, 2, 3, and 4. So obviously this polyline is not going to work for my purposes. What I need to do is I need to figure out a way to mix this list with this list so that the resulting list has this element, the first one, this the second one, this the third one, this the fourth one, fifth, sixth, seven, in a way that they are weaved into this pattern that does the internal triangulation. How am I going to do that? Well, we're going to see now in Grasshopper how to use weaving to put these two lists together into a one that has these elements woven. Sorry, I'm having projection issues again. Okay. Now, okay. Okay. No, again? Oh, seriously, this is so lame. Okay. Weaving is an operation that can be found under list. And then these other components that we have not seen, but that I very much encourage you to check out and to give them a try. They're actually very useful. And weaving is a component that takes two sets of inputs, two lists, and combine them using a pattern. So using something very similar to the technique that we have used for culling. So what does that mean? So it means that, let's take a look at the component. The component says, can I use a pattern of input indices, so 0 and 1, 0 and 1, etc. And then here under 0 and 1, we have the streams of data that we want to mix. Okay? What does that mean? It means that here I have already a pattern that is zeros and ones. So what I'm going to do is I am going to plug in here my first one, my first list, the points that were on the bottom. And then I'm going to plug in here on the number one, the points that were on the top. And if I look at those now, you can see that the order of the points is a little different. And then, but they are all combined under the same list. So I can now plug this list into the polyline, and you can see that, oh, something is kind of happening. So I do have some kind of triangulation. It's not the ideal one. And I think what's happening is that input 0 is the one that has 3 points, so the ones on the bottom, and input 4 is the one that are on the top. So what I want to do perhaps is I want to define a triangle, a pattern that starts by taking points from list 1 and then keep going and taking points from the list 2, because I think that what I'm doing now is the opposite. So I'm taking points from 0 and then I'm taking points from 1. And that's why I start here, go here, 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 and then end up here. So I'm going to change the pattern. I'm going to say that I want you to take a point from list number 1, this one here. And then I want you to take an element from list number 0, so the one that you have here. And then I'm going to make sure that this is multi-line data. I'm going to plug this in here. And then, ta-da! It turns out that we now have the right triangulation here. And let me play around a little bit with this, see if it's actually working. So I have more spans, so you can see that I still have the gap. And here, as I retract this, I get more and more gaps on the side, which is kind of great, all the way to 0, which creates these weird overlaps here, which are not great. So, yes, so 2, 3, 4, 5, whatever, you got it. This might be 4 now. This looks a bit more elegant. Okay, we are very close. So I'm just going to copy and paste everything for the right arts. So for the right arts, I would like to copy and paste all of this. So that's going to be, so that I have here for the top arch, now I have my points there, okay? And then here I'm going to create another polyline that is going to weave the points on the base, which are these ones, with the new points that I just created. So this one. And then I'm going to turn on that curve as well. Beautiful, beautiful. And let's not forget that I want to also create horizontal bars between the top members here. And that is actually going to be the easiest part, because I know that those points, I have them here, I have those points here, and I have them here. So what I can do is I can just create a line between 2 points between these ones and these ones here. And you can see that I now have the structure of the spatial truss. Wait, are we done? Is this what we wanted? Yoo-hoo! Spatial truss! And with 2 curves and arches and blah, 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 and all the good things. This is actually very, very cool. But I think we can spice it up a little bit and make it a tiny bit cooler. just for the sake of visualization, I'm going to indulge a little bit in adding pipes to kind of see like the thicknesses of, to kind of see like these elements with a little bit of thickness and perhaps do some renderings. So I'm going to go to surface, I'm going to do pipe, and then I'm going to place a pipe on, first I'm going to place pipes on the curves. So the actual curves. So this is going to be the base arch, the top arch, and the right arch, and the radius is going to be something that I'm going to control numerically. So the radius is going to be something very small, like this, okay? So that's going to be one thing. And then I probably, well, that's actually quite small. And then for the, so that's going to be one thing. Those are going to be one pipes. Then for the horizontal bars, I'm also going to do pipes. I'm going to copy and paste this, and I'm going to overlap it with this. I'm going to make them a little smaller. So I'm just going to do a slider that is start at 0.1 and yeah, something like this, much smaller. And then for the polylines, because they have angles, and if I do pipes, the angle of the pipes are going to overlap with the other ones, I'm going to actually explode these polylines into single segments so that the pipes have a clear start and a clear end. So I'm going to go here, I'm going to utilities, I'm going to go to explode, and as I do explode, you can see that the result is that I have, for this polyline, I have like a bunch of line-like curves, and for this one, I have the same, and then I can pipe this, I can add these guys to this rendering, for example, and then you can see how now the pipes have been rendered as part of, and then if I do some render visualization, for example, so let me bake this, and let me bake this. You can see that now it looks a little sexier, right? These pipes with some thickness, etc. That kind of looks pretty cool, as I may have to say. Not because I made it, but I think it's kind of cool. And last but not least, should we try the same thing that we tried before in the previous exercise, where we took all these curves and then we used them as the support for all this network of trusses? Let's do that. So I'm going to bring those curves here, 1 and 2. I'm going to set one curve here. I'm going to set the other one curve here. I'm going to divide the curve by a control amount of points. So for example, 20. And then I'm going to do the same for the other one. I am going to graft these outputs. Remember, I don't really like grafting outputs like this, but just for the sake of speed. And then, are we ready for this? This is going to be seriously cool. So we're going to add that here. We're going to add that here. And then, if I now bake all of this, you can see that, well, I can see that I can turn a lot of things off here and off here, a lot of points, and then I can see this network of, of arches, and with a bigger depth and a little bit of this. And then you can see how now, they now look like a canopy, like a structural canopy of elements. And actually kind of loft. What are the base arches? Can I flatten these and loft a curve through them? I can. Choo-choo. And so, and then if I bake this surface and I bake all these pipes here and I group them, and I bake all these pipes here and I group them, then I get my result is going to be something like this. Choo-hoo! Nice! Woohoo! How do we like this? This could go. This is a very nice parametric definition of some pavilion with some structure and like a little bit of structural logic, a tiny bit of optimization. These members are smaller, these members are bigger, etc., etc. And I can look. Wait. Ooh. Whoa. Okay. And I think with this, I think I'm done for the day probably. All right. Hopefully you like this exercise. Maybe it was a little long, but I think we learned a lot of things. On the way, I think we learned very interesting techniques. I think we got to see how data manipulation and smart data matching can be a really strong asset in our definitions and allow us to do really powerful parametric modeling, like the one that you just saw here. So with that, I am going to leave it here. I would like to thank everyone who has joined me recording this tutorial in the live streams that we do. Thank you very much. And if you liked what you saw, if you think you learned something from this video, maybe consider liking the video or subscribing to the channel and maybe even turning on notifications so that you know when we publish new stuff. Crazy, right? But in the meantime, thank you very much, and I will see you on the next videos on this series where I think we're going to keep doing more exercises because these exercises are cool. I think they're a lot of fun. Thank you very much, and see you in the next videos. Bye bye. Alrighty. I'm going to hide all of this. I am going to going to disconnect here because I need to record the introduction. Okay. Let's record the introduction. Huh? Are these not linked anymore? Oh. Okay. No. Hi, and welcome to this new video on the series Introduction to Parametric Modeling, where we're going to do a hands-on exercise, still practicing lists and still practicing ways of manipulating data for creating geometry. And in this one, we're going to do a super cool exercise, which is going to be modeling a spatial truss that is going to have an internal triangulation that is going to follow the Warren pattern. The Warren pattern is a pattern that looks something like this. This is the Warren truss, but we have chosen to do it in 3D inspired by some examples of, for example, the canopies of airports that typically display this pattern. So it's going to be super interesting. We're going to imagine that we're going to design some kind of like really structural canopy that has a lot of span and that it needs this really strong structure sustaining it. Of course, everything is going to be parametric. So the height of the arch, the depth of the truss, the width of the truss, and we're going to start from points that are going to be defined. The supports are going to be defined as points. And we will end up by doing a few modifications so that we can also not just apply this to two single supports, but apply this logic to a full two full collections of supports, so that we can generate this kind of pavilion looking kind of design that has all the 3D spatial structures on top of it, and which, if we actually bake, it will look something like this, which I find like a super interesting kind of exercise. We're going to learn techniques for this exercise, such as weaving data. We're going to learn techniques such as culling data. So if you've been following this series, we're going to learn a few new components that we haven't seen before. And it's going to be super fun, and it's not going to be that complicated to get this really powerful result. So join me in this journey of designing 3D spatial structures, and hopefully we will learn a lot of stuff together. Let's get hands-on. All right. Oh, I think I'm done for the day. I don't think I have the energy to do the facade exercise. We will do that tomorrow. Okay? Because what is tomorrow? Tomorrow is Thursday. When are we streaming? Are we streaming tomorrow? Yes, we are streaming in the morning and in the afternoon. 2 streams tomorrow. So yeah. Thanks to everyone. I have a couple minutes. If you have any questions, if you want to do Q&A, social, some comments, whatever. Otherwise, I will see you tomorrow. We are starting at 10 a.m. my time, Eastern time, Boston time, whatever that may find you. And as usual, if you subscribe to our Google Calendar, I left a link on the chat, or if you join us, if you follow us on social, you will be able to figure out when we go live. And if you join our Discord channel, our Discord server, we have channels where I announce when we go live, etc., etc. So you can just stay up to date with what we do throughout the week. Okay? And with that, I believe this is what I wanted to do today. I'm a little exhausted. I've been streaming for 3.5 hours already. Woo-hoo. That was a lot. Okay, well, it was a pleasure. Thank you very much, everyone. See you on the next stream, hopefully tomorrow. Otherwise, any other day, it's fine. I will not take it personally if you don't follow every single live stream. Thank you very much, and see you tomorrow. See you any other day. Bye-bye.